In this video, we're going to talk a little bit about vibrational modes. And so we've talked about excitations for electrons from your n equals 1 to your n equals 2. That you can have an electron and it can be hit by a photon and get excited up, and then it will relax later and give back off that photon. Well, energies change a little bit because we don't just have one or two states. We talked about vibrational modes, that there is a series of slightly different situations that this orbital can be in. And so our electron could be in the orbital, but that orbital could be at slightly different energies due to the vibrations. If it then excites, it has some options on where to go. As a result, you could go ground to ground, you could go ground to up higher, you could go from a higher to the ground, or you could go from a higher to a higher. Each of these has a slightly different height, which correlates to energy in this case. This is why we get a broad peak of absorbances, that despite the energy between orbitals in theory requiring a exact energy in order to go between, the reality is there's actually a series of very similar orbitals. The orbitals themselves are really one. Like, this is a single orbital. It's just that orbital could be in several vibrational states. What does that mean? Well, I just have two atoms. Here's an atom, here's a second atom, and they are bonded. But instead of a straight line, the original math for it treated it like a spring. And this isn't all that bad. Mathematically, it kind of works out. They can compress, they can expand, they can compress, they can expand. And so the two atoms can get shorter, push away from each other, stretch out, and then end up pulling back towards each other. And so you'll just go back and forth between moving out and moving in, moving out. Imagine one of those little wood paddle toys with the rubber band and the ball, and you hit it and it bounces away and then comes back. Because if you think about a covalent molecule, they start far apart and higher in energy, and they start going down in energy as they get closer together. And then there is some ideal where they are just the right distance. If they get too close, they start to repel each other and the energy goes up. And so we have a bond length, but if you roll two things towards each other and they're moving towards each other as they're getting closer and the attractive forces are pulling them in, when they get to the optimal distance, they still have motion. They've been moving towards each other. They have a velocity headed towards one another. The net effect is, even if your atoms, as they start getting closer, are following this energy path, they don't dead stop at the bottom. Like a ball rolling down a hill, it's going to roll up the other side, get pushed away, roll back, get pushed away. It's going to go back and forth inside the pit. Now, if you roll a ball into a curved thing, or a skateboarder on a skateboard or something on a half pipe, and it just goes back and forth a little while, you slow down. Friction will slow you down in the real world. You bump along things, you transfer a little energy that makes the noise, you push the air out of your way. Eventually you'll slow down, but an atom doesn't have that. There's nothing for the molecule to bump into. So there's nowhere to put that energy. And so it stays. The atoms can't get rid of it. So once they fall in, they just go back and forth. And they will continue to go back and forth for eternity. There's nowhere to dump that energy. As a result, they don't stay at one spot. What they really have is vibrational modes that tell the range that they'll jump back and forth. When you first come together, you might lose some of the energy in a photon, and you might bump into another molecule if you're a liquid. And so it's possible to be moving just a little bit, but especially if you have like free atoms in the gas phase, when they come together, there's really nowhere for the energy to go. And if you have a frictionless system and you roll the ball down the pit one side, it would roll up the other, and it would just keep going back and forth. Now we can ditch some energy. Like I said, we can give off a photon. This is possible. This energy difference, if we want to give off a photon, so we want to drop down and not go up above anymore, this is in the IR region. Infrared radiation correlates with the vibrational energies of these orbitals. This is why we talk about heat vision. Heat vision is seeing IR light, and that is what we tend to think of as heat light. If you have something that isn't on fire but it's given off heat over distance, that is infrared radiation. And in fact, even a fire is giving off a lot of infrared radiation. If you just feel heat coming off of something, but it's not blowing hot air in your face, or it's heating a molecule and throwing the hot molecule at you. If it's photons, it's almost certainly infrared radiation. Well, covalent bonds especially have a great deal of vibrations. They're sharing electrons, they're always moving towards and away from each other. It's not that you can't have these for ionic, you just don't have nearly as many or as significantly. Ionic compounds tend to have very little IR absorption because they don't have good vibrational modes. Covalents tend to have a lot more. In fact, we use this to great advantage. If you have ever seen somebody test a chemical to see what it is, we generally use IR light to do it. The units are a little funny. They'll be in reciprocal centimeters. It's wavelength converted to centimeter and then inverted, so 1 over. But the idea is higher numbers like 4,000 mean more energy in this case, and lower numbers like 500 mean less energy. And we'll do intensity. We'll shine light. We'll say, all right, here's pure light with no sample, and then we'll take a sample. We'll shine that same light through a material, and what we'll see is it'll absorb some. There'll be missing light at various wavelengths. Those wavelengths will correspond to particular vibrations. Things out in the, 3,500 to about 2,900 range tend to be OH vibrations. Things in the 2,800-ish to 2,700 are types of CH bonds. If you have carbon with a double bond to another carbon, then a hydrogen, well, that can show up here as well. Out in the 1,700-ish range, you get carbon double bond oxygen. And so on and so on. There are other, it's called the fingerprint region down here, tend to be a lot of CH vibrations that aren't the straight out and straight in. If you have a carbon and it has multiple hydrogens, well, these hydrogens can vibrate towards each other. So imagine holding your arms straight out to the sides and bringing them to the front, and then bringing them back to the sides, and then bringing them to the front. Right? Or weightlifting. Have your arms in front of you and just lift them up. They can go up and down. They can vibrate around. There's a lot of different vibrations that can happen when you have multiple things. That tends to be in this region for the CHs. Organic molecules have lots of CHs, so it's really useful. Every single compound is going to have a different pattern. If you don't have an OH, you'll be flat in that region, and then you'll have some CHs, and maybe you don't have a CO, but you do have a ring of carbons with double bonds. And so you'd get this different pattern. Every organic chemical has a different spectra. We call it the IR spectra, FTIR, Fourier transform, infrared. This is how we do a lot of chemical testing. Once we determined that light could be used to look at the vibrations, we no longer needed to do a dozen chemical tests to figure out what a chemical was. We could smear a little bit on a piece of quartz, shine light through it, see this pattern, and figure out what different bonds there are on it, what types of atoms are bonded, and if we had already scanned a known chemical, we might find a perfect match. If you got one and it looked exactly the same as another one, maybe your intensity was a little different, but it had the same peak values, well, it just meant you had a little more, a little less of the chemical. But if it had exactly the same peaks, it was exactly the same chemical. And so, not just for things like broadening of absorptions for our visible light, where we saw peaks in the visible, so 700 nanometer, 450 nanometer. As we saw in the Beer's Law lab, we had peaks like this that were focused out here in the blue and the green, so we saw cobalt chloride is more red. This was our absorbance in the visible. Why is that peak broad? Well, because it actually has a lot of little adjacent vibrational modes, and then each of those is smeared out due to Doppler effects to create one broad curve. If we can look at those vibrational modes in a little bit more detail, we can actually start to see a great deal of info about the chemical. And so there's a lot more going on with those vibrational modes that we can exploit than just broadening our absorption of spectra. That's what we wanted to focus on this point. What is actually going on in those extra little vibrational modes, and how on earth can we utilize it to our benefit?